is Mahdi Soltanolkotabi from the University of Southern California. Mahdi has won many awards for his amazing research in recent years, but instead of listing them, I'll talk a little bit about what it was sharing an office with him during grad school. We both had the same advisor. And professionally, that's maybe what I miss the most about my grad school years. We would sit side by side, and then when I had any question about any possible paper about signal processing, machine learning, sparsity, whatever, I could just ask Mahdi, and he would know the answer. Like he has an incredibly vast knowledge, and also he has incredible intuition, and you can see this in his works. So he did some very interesting work on subspace clustering during his PhD. Then he moved on to the analysis of non-convex optimization methods for signal recovery, such as in phase retrieval, and did amazing work there. And lately, he's been more interested in machine learning, and he's developing mathematical insights that allow us to understand better why certain machine learning algorithms, in particular neural networks, work. Yeah, and today he'll talk about that.
Nice introduction. I also kind of really miss the Stanford days these days. Actually, like this, in some ways, this actually is the second part of the talk, is somewhat inspired by the previous math seminar I was giving, because that's where I probably heard dip first there. So let me start by motivating the talk. Basically, okay, there we go. So this is joint work with the Zalom Fabian, who is a student at USC, Reinhard Heckel, who is like a colleague at TU Munich, and Samet Oymak, who is at UC Riverside. So there's kind of two motivations for this talk. One of them is basically understanding the benefits of early stopping. And so to explain this, let me just show you some experiments. So this first experiment you've probably seen often, which is basically having to do with the ability of neural networks to overfit to corruption. So what happens here is that you have a bunch of training labels, and then you basically corrupt a bunch of the training labels. So for example, if you have some zeros, you flip it to 8. Even though the true labels is 0. And so what you can do is, like, let's say you flip a percentage of the labels, and you want to see, okay, what is the training accuracy here? Even if you corrupt like 100% of the labels, and this experiment, again, you've probably all seen, you basically can perfectly fit this even though noisy labels. So they perfectly fit. Interestingly enough, if you look at like the test accuracy, the accuracy on the test data, it's still somewhat non-trivial. So it actually is not that bad, I guess, given that you're corrupting labels. Of course, the accuracy with respect to the true ground truth labels is pretty bad, right? Like it's going down quickly. So this just shows that the neural networks can basically fit anything, including corruption. But here's the interesting part, like that maybe you may not have seen, is if you repeat the same experiment, but stop early, right? Like, stop iterating early, then all of a sudden something really interesting happens. First of all, the test, the train accuracy goes down because you actually don't fit the training data anymore on the corrupted labels. But if you look at the test accuracy, it's really high now. And the orange curve is even perhaps more interesting. The train accuracy with respect to the true labels is consistently high. It's actually basically 100% up to 30–50% corruption. So this means that even though you corrupted some of the labels and the algorithm has never seen those corrupted labels, it actually automatically fixes it for you, right? So it actually gives you the correct ground truth labels even though it has never seen them. So that's kind of like the exciting part about this experiment. So this is the motivation number one, trying to understand what is happening here. So the second motivation is, in general, understanding kind of these so-called untrained networks. And And of course, we all know that neural networks have been extremely successful at learning from data. In particular, we could think about what plays a good, important role in the success, and there's many reasons probably. Some attributed to computation, but arguably one of the more important things here is the fact that now we use much larger data sets, and we have much larger data sets of things, and that's why they work particularly well, I guess. And if you look at basically what most tech companies do these days, or so-called AI companies do these days, it's fair to say they actually devote a significant amount of time to basically just gathering and curating data. In fact, this is like there's this New York Times article that actually goes into this and related issues at depth. It's quite interesting. So, and this is kind of fine, and there are a lot of applications where this is possible. Basically, you can crowdsource your labeling and things of that sort. And this is the case probably for computer vision, natural language processing, and so on. But this kind of data-centric approach may not always work in other settings. And in particular, the settings I'm thinking about is like, applications that have to do with the basic sciences, right? Like whether things that come up more in medical imaging or imaging in nanoscale applications, like like phase retrieval, you can think of it as sort of a toy problem of that category. In these kind of domains, each training data is the result of some maybe expensive or time-consuming experiment. And so you cannot, it's maybe not so easy to actually gather so much training data. You can't really crowdsource it, right? And then, there's also another issue here is that a lot of the kind of neural networks that we are used to in applications like vision, NLP, and so on, they're more or less classification based. In regression, as it turns out, like neural networks are much more prone to overfitting, and so at least currently, a lot of the tricks we have to avoid overfitting in the classification setting, does not work particularly too well in the context of regression. And so because of this, we may need some alternatives, especially if we start to look at these applications. And one possible solution that is kind of emerging is like the use of these untrained networks. So let me give you like maybe the simplest possible example of what I mean by an untrained network. So here is like one way people have looked at denoising using neural networks, for instance. So here you basically have an image, you add some noise to it, you get the noisy image. So the way you can use neural networks to denoising is kind of an unintuitive way in some sense, is that you take the noisy image and you try to fit a really large neural network to this noisy image. And because you're trying to fit a really large neural network with a lot of parameters, if you actually iterate long enough, basically this run gradient descent on this objective and iterate long enough, you can actually perfectly fit the noisy image, right? So that just shows again that neural networks have the capacity to learn anything. But the interesting part is that if you stop the iteration somewhere in the middle, you actually get the denoised image back, right? And so again, this is fascinating because you only the algorithm and the network has never seen any other image. It has not seen the clean image. It just sees this one single noisy image, and it still can be noised, right? So that's really like the interesting part here. And this experiment is actually like known as deep image prior, and I show pictures from the original paper. This is how actually like this goes back to the math seminar, because I think probably one of the first places I heard this from was from Carlos. But at the time, I didn't really know how to explain it. It's like only during the last year that I kind of we figured out what how one maybe could look at this more mathematically. So so the same picture basically, but if you look at the relative error or the denoising error as a function of the number of iterations, so you can see better here why this works, why the early stopping is key. So the error is large originally, but if you stop somewhere in the middle, the error is small, so you get a denoised image back. But if you keep on iterating, you eventually fit the noisy image. So this is why. And this is for these two different curves are for two different kind of networks, but essentially you see the same behavior. In the middle, somewhere in the middle, there is a range where if you stop there, you actually get a good denoising result, right? And so this is just one example of untrained networks, and I'll talk about more examples when we get to that part. You know, in one of the original papers that demonstrated this was this so-called deep image prior paper. They showed this kind of idea not only works for denoising, simple denoising, but it also works for removing all sorts of other corruptions. Like it works for in-painting, super resolution, removing text, all sorts of interesting phenomena. So you could actually use these untrained neural networks in this way. So to given these motivations, today I'm just, you know, to understand kind of these experiments, I'm going to focus on two stories. The first one has to do with classification and in particular understanding the robustness of these networks to label noise if you combine them with early stopping. And the second one, again, is more of a regression context, and it's like denoising, solving inverse problems using these untrained networks. And here really the common theme that kind of connects these two things is that you know it's really important to understand the optimization generalization not just at the endpoints but really the dynamics of it. So that's going to be basically our focus to see how you know the error or generalization error and also the optimization error changes across time. So the time component is really important here. And so that's the common theme. So let's go to the first set of experiments and trying to explain that, right? So here, this is the experiment where we added, you know, we randomly shuffled a bunch of the labels, and we saw that with early stopping, you still get perfect accuracy with respect to the true labels, and also in the test data. So we're going to look at like a simple model for this. Basically, it's a one hidden layer neural network model. So let's say you have a bunch of data points. The x coordinates are in RD, and you know, like the output is k-dimensional because you're looking at a classification problem. And you simply try to fit the output of the neural network to one hot encoded vectors, right? Like the labels are ones and zeros, right? One for the correct class, zero for the rest, right? So using these squares. And if you kind of aggregate all of these things together, it's just some gigantic, this nonlinear least squares problem. And so in order to train this network on the training data, what we're going to do is just run gradient descent. In this work, we also keep the second layer fixed. We only train over the first layer. You know, because it's a classification setting, what we're running least squares, what we're going to do is basically pass this through a soft max at the end. So you actually get labels back, right? Like so you pass it through a soft max layer once you've learned the network and then pick the maximum essentially. Let me also tell you what kind of data model we look at in particular in this paper. So we kind of look at somehow a cluster model, right? So here, what we're going to assume is that the data, the input data, right, they come from mixtures or clusters. So each class can have multiple clusters. So that is kind of the setup. And but that's kind of the idea, you know. Think about this like maybe you have a mixture of Gaussians, but each class can have multiple mixtures, right? So this is kind of like probably a reasonable assumption in something like MNIST because people have demonstrated that this is true. the results I'm going to present hold a little bit more generally, but we will discuss that when we get there. But so that's the data model. So we have L clusters, K classes, right? And L is much larger, typically larger than K. So again, we want to understand how does these networks do well in terms of robustness. So let's say you have like a clean data set that you start with, training data set that you start with, and let's say an adversary is allowed to basically corrupt a row fraction of these labels. So it takes the clean labels y bar and changes them to like yi, right? But it's only allowed to corrupt row fraction. And the way it's doing this is just assigning an arbitrary other label, right? Because it's K classes, it's assigning arbitrarily one of the other K classes to it. There's also some balancedness condition. You know, the adversary is not allowed to corrupt like just from one class in some sense. But other than that, there's no other assumptions on the power of the adversary. So again, we're just fitting this neural networks via gradient descent in a least squares loss. And so here is kind of like our theoretical result about this is that if the corruption level is smaller than a constant, 1/16, and the neural network is sufficiently over-parameterized in the sense that the number of parameters, total parameters of the network, is bigger than the number of clusters to the power 4, then something interesting happens. If you stop early, then what you can show is that the closest label to the output of the neural network is actually the ground truth labels, right? So again, you train using the corrupted labels, but if you run gradient descent and stop early, you actually get the ground truth labels, right? And this is if you stop after a certain number of iterations, which we specify. So again, this actually explains that experiment. You perfectly correct your corrupted training data and give back the true labels. So a kind of like a second component of this. Not only can you show this for the training data, in fact, you can show this even on the test data, right? And for this purpose, just basically define basically like this ground truth labeling function, which given any input, it essentially looks at the closest cluster center to it, and then assigns the class associated to that cluster. So this is kind of like the perfect, you know, if you had an oracle, this is what you would want to do, right? Like you would basically want to figure out which cluster it is in at least like a map setting, which cluster you're closest to, and assign that class. And so if you do this, if you have this, you know, define this ground truth label function like this, then again, under the same setting, you can show that, in fact, even on a new test data, basically you get the ground truth function, right? So you corrupt a fraction, you over-parameterize again, you stop early, and regardless, this should be X, by the way, regardless of what input data you feed it, if you stop early, and you get the ground truth function. So this also says that, you know, even on test data, you get basically perfect accuracy, at least if the corruption level is small. So I mean, basically as good as like the map estimator in some sense. So let me try to explain this, give you an idea of how this proof works, because it actually connects to also like the second part of the talk, as you will see. So what is the key idea here is actually like, it's basically, if you look at gradient descent iterations, right? If you're running gradient descent, if you think about it, what is the gradient here? It's basically somehow like this is kind of the residual, the output of the neural network minus the labels. And the gradient is basically that residual times like this Jacobian matrix, right? This is just the Jacobian of the output of the network with respect to the parameters. In this case, this Jacobian matrix looks something like this. So the key idea that kind of, you know, allows us to prove this, well, the key idea number one is that, you know, if you look at this clusterable model, if the data is perfectly clustered, what one thing that is kind of easy to show is that For example, if you know, you have L clusters and everything is exactly on top of those cluster centers, then the rank of this Jacobian is L by K, K being the number of classes, L being the number of clusters. So that's like the key intuition. One of the key intuitions is that this Jacobian is low rank. Of course, if it's not perfectly clustered, it's still kind of approximately low rank, right? If you actually have some noise around these cluster centers, it's still kind of approximately low rank. So that's key idea number one. In fact, you know, even though we kind of discussed these theorems in this setting where the data is kind of clusterable in some sense, you know, in fact, this property actually does hold on real data also. So that like this is a simple experiment on CFAR10 using like a ResNet 20 model. So you can see that if you look at the Jacobian of the network, this is on a just free classes, but I'll show you the same on all of the classes. If you look at like the Jacobian of the network, from initialization all the way to the final iteration, this Jacobian has this really nice property that basically there are tens of large singular values, but the remaining are fairly small, right? So you actually see some of the singular values really are popping out of the spectrum. So you can actually see that it's kind of approximately low rank in some sense, the Jacobian on the real data. And so this is actually going to be the key structure that pushes our proofs. This is, you know, this is more of a fancy experiment on the entire CFAR. This is not exactly the Jacobian because now you have much more data. It's not that easy to calculate the singular values, but this is kind of an approximation that we came up with. And you know, like we're looking at the just top 1,000 singular values, you still see like this low rank behavior again, if you look at the histogram. So the second key idea that is really important in this proof is that the prominent eigenvectors of the Jacobian are diffused. So they're not very spiky, right? So that's the second key idea, and I'll tell you in a second why that is important. So now that we have these two key things, so remember, key idea one was that the Jacobian is kind of approximately low rank on real data. The second one is that the top eigenvectors are not spiky, they're kind of diffused. So let's see how, if we combine these, good things will happen. So again, think about the like the gradient is Jacobian times the residual. So if we write the residual is like output minus the labels. If we write it as output minus the clean labels or the ground truth labels plus a corruption vector, so that now let's look at this residual, right? So we have the residual with respect to the true labels and we have the corruption. And remember, because we only corrupt a constant fraction, this corruption vector is actually sparse, right? Like, you know, it's only a constant number of entries are non-zero. So what happens here is that as we run gradient descent, you know, the residual with respect to the true labels in the first iteration actually goes down very quickly because this part is actually aligned with the top eigenvectors. So as you're running gradient descent, this part goes to zero very quickly because it's aligned with the top eigenvectors of this Jacobian. This second part, because the top eigenvectors are diffuse, is actually not correlated with the top eigenvectors at all, right? So this part actually mostly lies on the remaining eigen directions. And so this part actually picks up energy very slowly, right? So it will also eventually go to zero. This is why you can perfectly fit eventually. But this part grows very slowly, right? Goes to zero very slowly. And so what happens is that if you stop early, you kind of make this term zero, but you still essentially keep this term intact, right? So that's kind of the basic intuition how this works. So these two combined give you the conclusion. So that's the basic proof sketch. And you know, in fact, this kind of proof you can work it out in more generality, but you know, it's a little bit more difficult to interpret the conclusions. But basically, if you have actually any nonlinear model, you know, nonlinear or in fact even linear learning model here, as long as you basically have some assumptions on this function, which is essentially, the function has to be smooth. The Jacobian in some sense has to be low rank and diffused in some sense. Then if you corrupt a fraction of the data, you basically get the same conclusion in generality. So this kind of result could possibly, could even work on deep architectures. At least, this result, would definitely apply. I mean, the catch here though is that if we were to apply this result on a deep network, somehow this local smoothness constant blows up. So it doesn't exactly apply, but it is suggestive that why it could potentially be also true in deeper networks. Okay, so that's kind of like the first part of the talk, which focuses on like this kind of robustness property. And now I'm going to switch to untrained networks. But if there are any particular questions about the first part, I'm happy to take them now.
Hi, Mahdi. I have a quick question. So these properties of the Jacobian, does it depend on the random initialization?
The way we prove it for this easy clusterable model, yes, it's kind of we prove it on random initialization, and we don't actually and basically we show that in this clusterable model it's maintained across iterations. So that's the way it works. But I think it's just in practice it's just true. Like it's actually true throughout training. And although I don't know if I have tried initializing non-random, so it might not actually work. But at least if you initialize at random and keep iterating, it's definitely true. I guess another place where you could see why it could be true in general, regardless of initialization, might be, let's say, if the data lies on a low-dimensional manifold or something, right? Probably then it's also true, even without randomness. But yeah, so our result definitely is for random initialization.
Okay, thanks.
Okay, so if there are no other questions, I can move to the second part. So this one is like has to do with like again this denoising experiment. So this actually discusses a bit more. So again, the setup is you have a noisy image, you try to fit this gigantic network to it, but if you stop early, you actually get the denoised image at the output. So here's a slightly different view. Again, if you stop early, you get the denoised image, but here's some intuition why this works, and it's again connected to the previous portion of the talk. Is basically if you basically repeat this experiment with two different kind of images. First, you look at like a clean, noisy, noiseless natural image, like this Chef-Logan phantom kind of thing. Then you can see that you actually fit the image very quickly, right? You can fit this image very quickly. But if you feed it a noisy, pure noise, basically, the network takes quite a while to fit that network, to fit that image, right? And so that's kind of the intuition, right? Like somehow natural images you learn faster than noise. And this is kind of again the intuition why early stopping helps, because you learn them faster. Just want to say that this kind of deep image prior phenomena, if you use it in the context of denoising, it actually does give state of the art, right? I mean, obviously, denoising is has a very rich history, and so it's like it's not, the improvement is not substantially significant, but nevertheless, it actually does give you state of the art result. So this is comparing with like BM3D, which is something untrained, right? Like it's quite famously used in image processing. It actually works pretty well. So this does give you state-of-the-art performance, and as I said, it also helps you remove other corruptions.
Can I ask a quick question? Sorry, yeah. I'm interrupting again. Does this depend on the network being convolutional, or do you?
Right. Yeah, that's definitely key, and I'll discuss that too.
I see. Okay. All right.
So it's actually like it's very key, I think, and I mean at least we can see in our theory how this comes up. So actually, like if we want to talk about the theory, is actually two things that are key. Is, you know, what architectures enable this phenomenon, at least for natural looking images in some sense. And again, what is the role of early stopping? This one at this point might be a bit less mysterious to you, given the last portion of the talk. So let's talk about the kind of architectures that actually work well here. So, basically, let me discuss the kind of architecture we focus on, and then I'll tell you the relationship with prior work. So basically, the architecture we work on is kind of a simple convolutional network. It kind of has this pyramidal structure which always goes upwards, right? So basically, you have k channels at the input. So basically, you can think of these channels as color bands in the image, like the RGB color bands. So you put the images as columns of this large matrix, right? So different columns are different color bands. And so from one layer to the next, what you do is basically you apply a convolution. So this UI is essentially, like, think of it as a circulant or a subset sample circulant matrix. So it's encoding convolution. And then you also combine these channels with some other matrix, right? So you combine them from the other side, from some other matrix with some other coefficient matrix. And so this way you get the next layer, and you pass it through a relay, you get the next layer, and so on, right? So that is kind of the setting. So here, potentially you could actually learn both the convolutional layer and also like these parameters, this kind of weighing. But what we actually focused on in this paper was that we actually realized that you don't even need to learn the convolutional layers. You just need to learn these combinations, right? But basically, I shouldn't say learning because there's no training data. It's just fitting these basically coefficient parameters. So even a fixed convolutional kernel would work. So what is the relationship to prior work? So this you can kind of think of as like a decoder portion of the network. In the original deep image prior, what was happening was like there was a decoder and then there was an encoder. So you would go up and then you would come down again, right? My collaborator Reinhard Heckel and Paul Hand, they wrote this paper where they realized actually like this second part of the network seems to be not really necessary for these kind of deep image prior experiments to work. And I guess in this paper, one additional thing we realized is that you don't even need to basically learn or fit the convolutional parts. You can even use fixed convolutions. So that was kind of our kind of sort of practical insight that you don't even need to fit those. So for the purpose of theory, of course, we still can't really analyze anything deep or anything like that. So we just focus on one hidden layer version of this. And just to recap here, if you have a one hidden layer model, it's going to basically look like this. So you have the input B, which you can kind of think of as a different color bands or in whatever you have, and then you basically convolve it, and then you have the weighted sum in the first layer and the second layer. In fact, we're going to even fix the last layer again and just basically fit the first set of coefficients. So what we're going to do is essentially, and this is what is done in practice, the input, remember the output is going to be the labels is a noisy image. The input is typically either random or even identity. Okay, so we start from basically an input which is identity. We just train over the CIs and see what happens. So obviously, because we are working in this setting where there are only fixed convolutions, right? It's clearly these what these convolutional kernels are is clearly very important. And at least the way it shows up in our theory is that what happens is if you have a convolutional kernel, what is important is actually what we call is like a sort of a dual kernel. Don't worry about the complicated definition here. It's actually not that complicated. It's basically you calculate some autocorrelation of the kernel, you pass it through some nonlinearity, and you use the Fourier transform. So this is how it's defined, but let's not worry too much about the details of the definition. Essentially, if you have a kernel, you can think of there is some dual kernel associated to any kernel. And so the key property that is going to be very important for us is that this dual kernel should die out very quickly, right? So, for two of the typical, for a typical kernel, which is like the simple upsampling kernel, convolutional kernel that we use and is also commonly used in this kind of setting, you can definitely see that this holds, right? This is for different bits, but essentially they die out very quickly, right? So that's kind of the key part. Like some dual kernel, which there is a formula for it, it has to drop down very quickly. So that's actually very key in this, and we'll see why. And the second part is, of course, you cannot denoise just any signal with this, right? Like the signal has to have some structure. And so what are the structures we look at? Is basically, for now, we look at a very simplistic signal structure, which is signals that are kind of low pass in a trigonometric basis. For all practical purposes, you can think of this as a Fourier basis, except that it's not exactly the Fourier basis. So it's very closely related, but it's not exactly the Fourier basis. But it does really look like a Fourier basis again, and it's really close to it in some sense. So we look at signals that are low pass in some sort of trigonometric basis. So that's the kind of signals we look at. And so now that kind of I've told you what the signal structure is and the architecture is, let's just go to the main theorem. So here's the theorem for denoising. If you have a noisy signal, basically signal plus noise, and let's say the noise is Gaussian. Again, the signal is it spans like the low frequency, P lowest frequency trigonometric basically functions. If you fit a generator like we discussed, where like the convolution that has like this dual sigma kind of thing, then if the network is sufficiently over-parameterized, if you stop somewhere early, the distance between basically the network output at that time minus the ground truth image, right, the noiseless image, actually goes down like P over square root of P over N, right? Which is kind of what you would expect in this kind of simple setting. If the signal has like P degrees of freedom and the total dimension is N, you expect like this square root of P over N behavior, right? So, essentially like the final conclusion here is actually pretty simple in some sense. If you have a one hidden layer networks with a convolutional generator with early stopping, essentially what they're doing is like Fourier thresholding, right? Which is kind of good. It also connects to like sparsity and so on. But obviously, like, actual, if you were to use actually a deeper network, they're doing something more nuanced and interesting. Like Fourier thresholding is not that great of a denoiser, although it's not so bad either. So it turns out that, like the basis functions that you learn in a neural network are actually more complicated. So they're not exactly like this simple, basically trigonometric structure, but you can see they're not that far off. They're definitely more nuanced and they do more interesting things. But you can even see that like in a 3-layer network, they're somewhat correlated, right? But again, like for an actual deeper network, obviously they're doing something more interesting. We don't completely understand what they're doing yet, but hopefully maybe in the future. So that's kind of the result for denoising. And so let me again give you a brief proof sketch of how this works. It's actually kind of related to the first set of results also. So to understand this, let's just look at just a linear network, right? Like pretend you're just denoising using just a linear matrix, right? So you have some noisy image and you try to fit a linear model to it. And so you stop at some, you run gradient descent, but you stop at some iteration. And so the estimator of the image would be that matrix times the parameters, right? So, and let's say this matrix J, basically J transpose J has an eigenvalue decomposition that looks like this. There's actually a fairly easy thing to prove that basically if you look at this output of the network in some sense minus the ground truth image, then there are two components to it. There's this first term and then there's a second term. So let me tell you what these terms mean. So the first term, you can kind of think about it as error in fitting the signal. The second term as error in fitting the noise. And so if, again, if the two key properties that we discussed hold, if the signal is structured, meaning like X is in the span of the top basis of J, and J is low ranked, meaning like the eigenvalues drop down very quickly. So if you look at this term is much, much smaller than 1. So if you iterate, even if you do very few iterations, this term goes down to 0 very quickly. Because, this matrix has this low rank structure, the remaining eigenvalues are actually very small. So this term is actually practically 1. And so this term is practically 0. And so if you only do only a few iterations, you never fit this noisy portion. So you never kind of see this noise at all in the first few iterations. So again, the intuition is kind of, even though the details of the proof is different, is really very similar to the first experiment. So here's this was for the linear case where we looked at the linear case as a warm-up. It turns out that it's exactly the same story essentially holds in the nonlinear case. So here again, the output of the network after certain iteration minus X, you can essentially think of it as something like this. You have an error in fitting the signal. You have an error in fitting the noise. The error in fitting the signal goes down very quickly, but the error in fitting the noise goes up, slowly. And so if you stop somewhere in the middle, you hit the right sweet spot. And again, I just want to emphasize that what is key here is two things: that the signal is on the top trigonometric basis, so it correlates well with this portion. And again, because this dual kernel dies out very quickly, this term goes. So unlike the linear case where everything is driven by the eigenvalues, right, of that matrix, now things are driven by this dual kernel. In fact, these dual kernel, you can think of it as an approximation to the eigenvalues of the Jacobian. So that's essentially what is happening here. So slightly different picture to maybe see this. So here I'm looking at the signal in the different components of this trigonometric basis, right? So this is the overall error, and this is the error in fitting the signal and fitting the noise. So you can see what is happening here is that the portion on the signal side goes down very quickly. So if you stop somewhere in here, most of the error in fitting the signal is gone already. You have picked up some noise, but not a lot, right? But if you keep iterating, all of a sudden you pick up a lot of noise, right? And so this is really why you want to stop early, because you pick up the signal components, but no noise component, right? So that's really what is driving this general kind of proof. It turns out that this also works in compressed sensing. It's a little bit more complicated, but essentially it's a similar story. Now, if you want to use like a network in kind of an inverse problem, it turns out you can basically do the same thing. So you have measurements now from a signal. You just pass the output of this convolutional network through those same measurements essentially, and you just fit this. So here the interesting part is that you don't even have to early stop, it seems. I should say, early stopping is less significant here. Here, in fact, even if you iterate to convergence, the output of the network is still good. And so here is like, a sort of informal theorem about this. So if you have a sufficiently over-parameterized two-layer convolutional generator, like the kind we discussed, if you run gradient descent on this, with x being kind of, again, a signal which is p smooth, again, p components in the trigonometric basis, then you can recover it with essentially order p random measurements. So that's the kind of conclusion. But let me show you like more experimentally how this works, how this looks. So at the time we were kind of rushing for a deadline, so we didn't actually do MRI experiments. So we worked with a smaller data. So this is like vegetable MRI, right? So it's not actual MRI. So they actually this data set actually takes MR images of vegetables. So you can actually see the phenomena. The loss with respect to the image, basically the error with respect to the true image goes down and then stays steady. So in some of the experiments, this goes up slowly a little bit. So early stopping sometimes helps, but it's not very significant. So this is kind of the interesting part here, is that unlike denoising, somehow because of the randomized nature of the measurements, you don't necessarily even have to early stop in a compressive sensing scenario. And I didn't really discuss this too much, but there's more detail in the paper, and I'm happy to also discuss this in the questions. But let's also look at how this actually works on actual MRI data. I actually don't have results from my own group, but we're still working on this. But my collaborator and his team have actually done really good work on this. And so here is basically, this is what they call the conv decoder. So they compare it with some of the traditional algorithms you would use for MR, like TV minimization, and even a trained network, but trained using like the simpler networks, like the UNet. They actually show that even though you don't have any training data, this conv decoder, basically this untrained network, can basically match the performance of what we were, I guess, doing a few years back with TV, and also like even a trained network. So here's another set of results from Mickey Lustig's group that basically show something similar. This paper, I guess, is going to appear in ISMRM, which is like the MRI conference. So they essentially show something similar in a compressive sensing setup where you accelerate by sampling fewer things. And these kind of untrained networks actually do seem to work well. It's still, I guess, with the kind of networks that we've looked at, we haven't been able to completely match like the state of the art using trained methods, but we're kind of optimistic that maybe eventually we could do this. But at least hopefully it's clear that it beats basically simple trained methods and some of the classical approaches like TV, which is like a really good baseline usually. So basically, to wrap up, so I talked about two things. One has to do with early stopping and how it helps remove label corruption in a classification setting. And we also saw that in a regression setting, it also allows us to denoise, again, without any training data. Similarly, you can use these untrained networks as the regularizers effectively in inverse problems without any training data. And so here are the papers, and so I'm happy to take any questions now.